All right, folks, good evening. Thank you all for being here. My name is Emmanuel Fonseca. I work as an assistant professor here in the physics and astronomy department. So thank you all for coming to these events. We're truly grateful that you come out. And again, we've been kickstarting this series as of last time. Sean gave an excellent talk on black hole physics and why black holes are really cool. And obviously today we'll have this talk, but then it's going to be a regular series. So from my understanding, there's going to be another talk in about a month. Is that right? And do we have an advert for that or no? Not yet.
I'm not sure if it's December 13th, and then it's the second Friday of every month.
Okay, nice. Nice. So yeah, we'll be putting out information about the next talk shortly. But yeah, again, please tune in because there's going to be all sorts of fun things to talk about on the astronomy side, for sure. So ironically, I do not study the sun per se. However, again, as an astronomer, as someone who likes to study not just physics, but the universe at large and so on, it's really easy to look far away, right? Because the cosmology, the universe as a whole is super cool. But it's also really nice and fruitful to look a little bit more closely and to see what sorts of things are around us, right? So I wanted to actually focus a little bit on the sun today because, at least for this past year, with the total eclipse that happened in April, the sun as a thing has been in the news and something people have paid a lot of attention to, but it's actually got a really rich and interesting history as well. And hopefully the things I will share are things maybe you've heard of anecdotally or maybe might be totally new, but there's all sorts of different ways in which we as people on this earth have interacted with and understood and used the sun to make sense of physics in general. So for my talk, again, as it's titled, it's called A Brief History of Solar Eclipses, or Waiting for the Sun, which is a reference to a Doors song, if anyone knows who the Doors are. There's a total eclipse of the heart. It was an obvious reference, but I try to make a little bit more of an effort. But again, as a PSA, it's kind of facetious to say because the sun's there, it's always there, etc. But I have to be the one to tell you, whatever you do, whatever you take away from this talk, which I hope is many things, don't look at the sun. It's this incredible thing, but given the amount of energy and radiation it outputs, it can really damage your eyes very easily, very, very quickly. So as folks may have remembered, if you interacted with folks here for the total eclipse event that was on campus some time ago, there are special glasses you can wear. There are telescopes designed to only receive a tiny amount of radiation from the sun. And those are all really cool things to engage with. So I encourage you to seek those out. Ask us here if we have any of those resources. It's, again, looking at the sun with the right technology is an amazing thing. But please, don't look at the sun directly. And if you have any questions, again, websites like NASA, the Canadian Space Agency, and so on, they have really excellent online resources for figuring out ways in which you can actually observe the sun while not looking directly at it, okay? Alrighty, so again, as I mentioned before, one of the reasons I wanted to talk about the sun itself is because it's there, right? And it's this it's this constant source of light for us. But when you actually look at the sun itself with, again, sufficient technology, you can start to see really interesting things that, again, are occurring in our neighborhood, right? And so it's shown here as a time lapse taken just 3 years ago of some activity around the sun that corresponded to a prominent sort of period of activity in the sun's life. And you can see the sun is an active thing. It's very much a living thing, so to speak. If you think of a star as a person, people, we are conceived, we're born, we live, we grow up, we grow old, we die, and so on. And stars like the sun very much live lives like that. And so you can see the sun being in its active kind of adolescent stage. But again, excuse me, only in the past, in the relative history of human civilization, only in the past recent while, which is, many hundreds of years, have we started to make sense of how we can understand the sun, how it works, and how we can observe it in slightly different ways. So as is mentioned or referred to in the title of this talk, again, earlier this year and in general, we tend to observe the sun most easily through what are called eclipses, right? And these are instances where you have this neat alignment between the Earth, the Moon, and the sun, such that the moon blocks some fraction of the radiation that we get from the sun in general. And again, this diagram has a bit to it, but the idea is that depending on the time and the distance of the moon relative to us and so on, and depending on where we are on the Earth, we will actually be able to receive or have blocked by the moon some amount of radiation from the sun. And only for a very, very small point on the Earth will we actually observe what's called a total eclipse, where the moon completely covers the sun relative to our perspective. And I don't know if folks have, like earlier this year, I think there was this TV show on Netflix called The Three-Body Problem. They use a lot of lingo. If you have seen it, they use a lot of lingo, one of which is syzygy, and it's a nice, fancy, fun word to use for a specific kind of a celestial alignment of massive bodies, so to speak. So in terms of what an eclipse is, it's conceptually quote-unquote simple. It's just the alignment of things such that we perceive a specific kind of an event, right? Now, for folks who may or may not be aware of the kinds of eclipses you observe, there actually are a few different kinds. Because of the fact that the moon is not at a constant distance from the Earth, it undergoes what's called an elliptical orbit, where it goes around the, the Earth, but not in a perfect circle. It's kind of a squished circle, so it comes closer to us, goes farther away, and so on. And so depending on the alignment of things, where things are in their respective orbits and so on, during an eclipse, you may see one of these situations, basically. Because again, it also depends on where you are in the Earth and so on. So again, earlier this year, a lot of folks in the United States were exposed to what's called the total eclipse. And again, that's when the moon essentially is close enough such that it completely covers the sun for a brief moment. But oftentimes you may observe what's called an annular eclipse, where the moon gets right in front of the sun, but is far enough away such that it doesn't completely block the sun as a whole. And therefore you get this kind of circular annular disk or ring kind of pattern that you see in the middle. And what was most commonly observed, in fact, by us here in Morgantown in April, was the partial eclipse. And that comes from due to where we are in the Earth with respect to an eclipse. We're kind of offset far enough such that we don't see, complete blockage, but we'll see some fraction of it, okay? And all of these are interesting in their own right, for sure. But again, as you can probably figure, the total eclipse is probably one of the most interesting. And forgive me, the room just lit up in front of me. Here's a sort of fun, it's very wordy, but it's a very fun graph taken from a very prominent kind of like science-y periodical called XKCD. For folks who haven't heard of it, it's a really fun, they'll take like little fun science tidbits and spin it into some kind of like topical thing of the day. And this was one put out, I believe, earlier this year, or at least like during a recent eclipse, where it kind of shows, okay, in terms of time, which is on this horizontal axis here, and then coolness, so to speak, on the vertical axis, you can see that as time moves forward around the time of an eclipse, you'll actually see, the x-axis, the horizontal axis is not so much time, but where you are located with respect to the location of a total eclipse, which is called totality. And so the idea being, the joke here being that it's really cool in general, but it's most cool when you're in that path of totality where the moon completely blocks the sun because of how dramatic of a thing you see, which is you just essentially don't see anything. It turns to night very, very quickly and for a brief period of time, right? So even though wherever you observe an eclipse, it's always a really cool natural phenomenon, totality is itself a really unique thing and experience too, as I'm sure folks will tell you. So shown here is an image taken from NASA, I believe, of the eclipse that occurred in April. And if you look closely, you'll see kind of these funny patterns like at certain parts of the ring around the moon as it's blocking the sun. And those are actually real structures of matter that are being emitted by the sun. Basically, they're called solar prominences, but they're basically just streams of plasma, right? Plasma being what's called the fourth state of matter, being ejected from the surface of the sun due to the magnetic fields present within that star. And you can see that during this time, there's actually stuff you can observe. And as scientists like myself and folks here at WVU, whatever we can see that is like not expected or interesting, we're always going to want to make use of that information. So even though eclipses in general are, again, naturally simple things that just occur when the alignments are right, it turns out that when they occur, depending on how the alignments go, you can observe really interesting natural phenomenon. And that, again, from a scientific point of view, is a really useful circumstance. And later on in the talk, I'm going to at least give a few examples as to how the sun itself and even solar eclipses have been very famously used scientifically. So again, in April of this year, this was the path of the totality of the eclipse. Okay, so this is a picture of the United States. You can see all the different states and so on. And that orange kind of curved band there shows the path in which, if you were in that region, you would have observed a total eclipse. Okay, so this is a very narrow strip, not at all that big. And again, Morgantown isn't terribly far away from here. It's like somewhere around here, right, close to Erie and Cleveland. But you can see that, again, if you wanted to catch totality, you would have needed to have figured out where to be within this strip, right? Now, it turns out, again, there are a lot of folks out there who are really passionate about observing eclipses, because, again, total eclipses are not as common, right? Because that's where the alignment has to be most right. So, again, we live in the era of data, and when you go search through data and ask the question, for example, you know, how many Airbnbs were booked during that time, you would see that this figure shows you the density of Airbnb bookings on that weekend, right? And so again, if anyone here is really interested in like aggregating data and you know, studying trends and so on, you would say, oh, there's a trend, something's going on this day, right? What could it be? But again, turns out, again, for folks who are really passionate about things like eclipses, these bookings were made almost 8-10 years ago. Because again, with our technology, we can predict when these eclipses occur, and they're so popular that people have already booked their hotels and Airbnbs for the next one, however many years it is from now, right? A long while, I can't actually remember the date. But you can see, again, even just with this simple graphic, you can see, oh, well, people don't really feel like going to the Midwest at the moment, and oh, there's this huge strip where people really want to hang out in for a specific weekend. But again, like I said, I'm not, so just to be clear, I'm not a vetted, trained historian. I'm a scientist, of course, but whether it's the sciences, whatever field you find yourself interested in, that field will have really interesting moments in history, right? Whether it's in the sciences, mathematics, economics, whatever things you like to think about and study. And again, astronomy is no exception. There's a lot of really famous moments in the field. And astronomy, especially because of its connection to the cosmos at large and natural phenomena that occur outside of the world, looking at historical records is really interesting, because it turns out that when folks were starting to kind of tread on that path of, you know, developing and using the scientific method and undertaking scientific inquiries, people were starting to jot down, hey, we saw this thing at this part of the sky at this time. And thousands of years later, like today, people are like, oh, that must have been this supernova event, right? And again, eclipses are no exception. So the quote-unquote first eclipse, which isn't actually the first, right? Because this is a naturally occurring phenomenon. The moon's been around for millions of years. But the first recorded solar eclipse by any person on the Earth was something like 4,000-ish years ago, around 2000 BC. Confucius himself, or at least as someone who then Confucius had records to their notes, jotted down that on some specific day around 2000 BC, there was a specific moment in time where the sun and the moon did not harmoniously meet in Fang, and Fang is the Chinese equivalent of a specific constellation, Scorpius. Okay, what we now know today to be Scorpius. So in these old historic records that again go back 4,000 years ago, was the first noting of what we now interpret to be an eclipse, where for some reason the sun and moon disappeared jointly or something like that. Something happened such that the light that was typical for any human being went away for a brief moment, right? So again, in these old, ancient, historically important documents, people were interested enough because of how dramatic that phenomenon was, right? But during these times, people didn't have the tools or the means to predict when these things would occur. Again, science as we now know it didn't really exist back then, right? So there was a lot more, for lack of a better word, mystical association with these sorts of events. So I think because of that lack of knowledge that, again, human beings develop slowly but surely over time, when you look at the historical records of eclipses that occurred and were recorded by people in some form or another, there's always some amount of anxiety that's associated with that event because, again, it is so dramatic, and back then people weren't really knowledgeable as to how to predict the orbits of things and alignments of things and so on. People literally thought, oh, this is a sign from God. This is somebody doing something to us, indicating that they're mad at us or something like that, right? And so you'll see oftentimes paintings that portray eclipses where people are losing their minds because they think something's going down, the world might be ending, and so on. And so when you look at historical records, whether they're historical purely or even associated with religious texts, eclipses play an important role, and they're often noted and associated with key moments in a person's life, in the time of some dynasty, etc., and even military practices, as I'll talk about in a second. The word itself, eclipse, actually comes from a Greek word shown here as eclipsis, which means abandonment. So again, the word itself, an eclipse, is meant to evoke that we are being left behind, so to speak, by somebody, something, what have you. And again, for historically, a long, long time ago, when an eclipse occurred, it was associated with fear. Okay. Now we have a lot of fun with it, but again, back then that was not the case at all. And again, as an example of just what kind of role eclipses played in mythologies in general, shown here is an illustration of a classic story from Norse mythology, right? So the mythology developed by the Vikings and so on, where their mythological interpretation of what happens during an eclipse is basically shown here. You have the sun, which is portrayed by this person on a chariot named Sol, as well as their companion, the moon, named Mani, being chased by two wolves, they're named Skull and Hati. And basically an eclipse occurs when the wolves consume both of them at the same time. Okay? And again, this is one of many different types of religious mythological interpretations, because again, back then, that's what all people knew, right? The scientific method wasn't really being developed as we now know it until many hundreds of years ago, but we're going back thousands with stuff like this, right? So again, people's understanding and the historical presence, so to speak, of an eclipse had undergone dramatic development as things became more understood and more sophisticated. But like I said, even when it comes to things like military practices or moments in history that involved conflict, the eclipse is actually solar eclipses are quite famous with playing a role in those sorts of moments of combat. And whenever you look up fun facts about the solar eclipse, you'll oftentimes see references to a specific battle referred to as the Battle of the Eclipse, I think, or the Battle of Halis, I guess more specifically, where armies from the nations that we now know to be Turkey and Iran were battling each other in a specific place that apparently during their battle happened to have a total eclipse occur in that spot, or in the strip as we saw in that graphic. So totality just happened to coincide with the location of a seemingly decisive battle that they were fighting, but then when, during the battle, when the eclipse occurred, it was such a dramatic thing to observe that it literally led to a ceasefire. It led to a stopping of the battle because everyone was so afraid that they were basically upsetting their shared God, or just something was going on that was telling them, you need to stop doing this. And so this specific battle is famous partially for this physical phenomenon occurring during the battle, leading to it actually ending and leading to a truce. So that's why I say solar eclipses for the win, so to speak, because it led to this cessation of hostilities. The other reason, though, which I note here at the top, as to why this specific eclipse was famous is because this is, again, the record that was maintained by Confucius that I mentioned a few slides ago. That's the first instance where an eclipse was recorded, like written down in a book somewhere, right? But this eclipse, the eclipse of Thales that happened like 1,500 years after that, was the first one that philosophers actually predicted. Now again, our understanding of physics as per the laws of Isaac Newton and so on wasn't at all established at this point, but people were at least starting to notice there are patterns to how things occur, right? In terms of, where the planets are located on the sky, when they appear again in certain points and so on. people were starting to develop an understanding of establishing these patterns and using them to predict when something that occurred on this day would occur the next time. And so people were starting to develop these tools, and this specific eclipse that coincided with this battle was also the first time that people were actually able to take previous measurements of eclipses and accurately predict, hey, there should be an eclipse around this time, and it happened. And again, as of now, given the technology that surrounds us and what we're exposed to, that doesn't sound particularly remarkable, but you have to, as much as we can, transport ourselves back to what it would have been like to have lived at that time, right? Where we don't have access to phones or TVs, or our sense of technology is not at all what it was then. And so to do something like that was truly Herculean, for lack of a better word, right? To actually use nature in that way was really dramatic, right? And again, physics as a field that a lot of us here study in the department has lots of really awesome moments like that. Even like, when you read into the discovery of, I think, Neptune, the planet Neptune, like it was actually theoretically discovered. People had already observed a lot of planets, and Isaac Newton has developed his ideas, and people took his ideas and said, hey, given the way that these planets in our solar system are moving, they're moving such that there must be some other farther away planet than those that we know of that's causing them to move funny. And it turns out that they found Neptune that way, right? So again, this was one of the first moments where that sort of predictive power was coming out, okay? Now again, this is an example of eclipses for the win, right? Some good happened, all that great stuff. But it turns out that there are also moments where eclipses were used for not so good things. And when you also look into the history of eclipses, oftentimes you'll read into the story of Christopher Columbus, again, the guy who discovered America, 10 or so years after discovering America, went on to sail to Jamaica, what we now know to be Jamaica. And the story goes that, again, the tribal folks on the island of Jamaica were basically convinced by Columbus that he had some special sort of preordained deity-like powers to him because he had, the benefit of technology and the prediction powers from measurements made by other folks over the millennia or the hundreds of years to say, hey, I, as Christopher Columbus, want to curry favor, if not have some sort of power over these people, and I'm going to trick them into thinking I'm a god by accurately predicting a solar eclipse that is going to occur on the island at this time. And the story goes that he actually was able to convince them to help him and his workers for a long, long time because they were afraid of him because he did something they could not, and they couldn't explain, right? So in that sense, I say, well, okay, that's not the nicest thing to do, to say the least, right? So, but again, we were developing this understanding slowly but surely as a way of, again, building our sense of how nature works and how do we use that information to gain better understanding of things, right? Now today, again, when you read into modern day portrayals or usages of eclipses, it's a little bit more fun, right? So for folks who grew up in the 90s and watched shows like The Simpsons, even watch anime like Sailor Moon, or for anyone who's a fan of the actual the Twilight Saga, so to speak, eclipses actually show up all over the place now in the way in which we convey stories, the way in which we have our media. And so they play an important role from a cultural point of view. But again, nowadays, given the advent of the technology we have, it's not so much as technologically useful now as it was back then. But it's still very fun, as you can see here, right? And as you can see, even Sailor Moon and Tuxedo Mask are using glasses, like I mentioned earlier. So please do always wear protective eyeglasses when you are trying to look at the sun. Okay, be safe. Alrighty. So before I move on to the scientific history of the eclipse, a fun fact is that I gave a different version of this talk for a buddy of mine and his startup company in Montreal, but I did so remotely. And the day of the eclipse, I didn't plan it out to be this way, but I was visiting my home back in the Northeast, and it turns out that the timing of the eclipse coincided while I was in the air, which was sort of a bummer, but I had, I was on the right side of the plane, so I was happy about that. And a lot of the folks around me didn't realize an eclipse was happening, and so thankfully I had glasses with me, and so I took the glasses, stuck them in front of my phone, and spent like I don't know, 40 photos worth, just trying to get a shot of the eclipse on my phone. And this is the best one I could take. If you zoom in, you'll actually see it partially eclipsed, which is very neat. But it was fun because I ended up sharing the glasses with folks around me. We switched seats. They got to look at it themselves a little bit. It was a good time for sure. And even though I was not in the path of totality during this time, you could actually perceive it getting slightly darker. Again, it's most perceivable when you're in totality because it just gets dark, period. It turns to night for like a few minutes, right? Not so much when you're not in that path of totality, but you can see, it gets a little dimmer and then it gets brighter again, right? So that's always really fun. So like I said, the eclipse, or rather the sun in general, as our technologies have improved over the decades and centuries even, has increasingly become itself an important laboratory, right? I mean, astronomers, a lot of us like to study stars of different kinds, ones in our galaxy, if, maybe one day those in other nearby galaxies like Andromeda, for example, but our own sun is really one of the key things to look at because it's right there. It's the closest star to us. And in fact, I remember when I was when I was taking my undergrad degree at Penn State, again, being an astronomer, you're so, thinking of like the things that are far away and all these fun, grandiose things like galaxies, the universe, dark matter, dark energy. And our like third year professor would ask us, hey, what's the closest star? And we'd be like Proxima Centauri or this other star, that other star. And none of us said the sun, So it was a nice exercise to remember that, hey, there's this thing just right over there that itself is this, bubbling, like fusion reactor, right? It's a unique source for our understanding of how nature works, right? And so with that, the sun has been and continues to be an important place for folks to study from the Earth with special telescopes or to launch satellites and have them head towards the sun itself. And shown here on the right is an example of such a probe called the Parker Solar Probe that is literally intending to and is orbiting the sun pretty close by, such that it's actually there to study the plasma, the actual matter that's being emitted by the sun over time. And again, the sun has played an important role in our understanding of modern physics in general, particle physics. Again, if you look into the history of physics, at least a couple of Nobel Prizes have been awarded for people studying the sun in a specific way. It's played a really interesting and important role in our understanding of how physics works. But believe it or not, eclipses themselves have been hugely important for understanding modern physics. And so as a specific example of that, when you look up, for folks who are interested in learning about Albert Einstein or his ideas of how nature and gravity work specifically, Einstein is most famous for developing what's called in our field the general theory of relativity. It's the modern understanding of gravity as a interaction force, so to speak. And again, technically it's not a force, according to general relativity, it's the warping of space and time that are unified in this paradigm. But again, when you transport yourself back to the time of Einstein, his idea was so dramatic that people didn't really take to it per se, because again, like a lot of movements, historical movements, things take time to kind of snowball and lead to this avalanche of new ideas and new things. And Einstein's general relativity was no exception. But to Einstein's credit, and like any good theory of physics, if you propose an idea for how the universe works, it's got to do three things. It's got to describe what's going on, it's got to explain it in terms of fundamental principles, and it has to predict something else, right? When you take your idea and you apply it to scenario A, and you can explain all that, but then you apply to scenario B, what else does your theory say about this new thing? Can it explain something? Can it predict something else that hasn't been observed before? And one of the earliest predictions that was made with Einstein's general relativity was that the warping of space and time by a star must also lead to bending of light, okay? And so this effect is generally called gravitational lensing, and I'll describe it in a second. But the idea is that when Einstein proposed this theory of general relativity, it passed an initial test or two, but it's needed to explain something totally not necessarily explained before, or at least, as a way to differentiate itself from Newtonian gravity, say. People were really interested in seeing how can it perform better, explain something different, be more accurate, and so on. In other words, be right, right? And so folks said, hey, according to Einstein's idea, if you take, light from a star that's behind another star, then that light should be bent, and we should observe things to warp appropriately. So people took this prediction and thought up, hey, how do we actually see this in nature, right? We can't stare at the sun. It's going to, burn our eyes. It's going to fry our technology. How are we going to be able to observe it? And people realized, hey, solar eclipses actually allow us to do this, right? The solar eclipse will block the light from the sun, so we can point our cameras at the sun as it's being totally eclipsed. And then in that time, because you're essentially in the night, so to speak, you can see where stars are, locate where they are, and then just compare those positions you measure with other ones that are observed when the sun's not there, right? So again, as a schematic to talk about what I mean, this is a simplified diagram of what gravitational lensing is. Again, the idea is that if the sun, which is that kind of blue thing there, if the sun is not there, then we wouldn't see this warping, right? We have some star, the white star, we can call it that its true position and emits light, right? The idea being that due to the presence of the sun, the warping of space and time by the sun will cause the light ray to slightly bend around it such that when we receive it on the Earth, it would have appeared like it came from somewhere else, okay? And that's gravitational lensing in a nutshell, okay? Again, I don't expect you to fully understand the effect per se, but the idea is that the warping of space and time leads things to, again, be warped and have their locations change in this case, right? And so the idea was, can we use a solar eclipse when the moon here is located in between the Earth and the sun to actually observe that shifting of the star's position that happened to be next to the sun, so to speak, around that time. And so folks actually did undertake this, literally an expedition, transporting yourselves back to 1919, very different time, 4 or so years after Einstein had proposed his ideas. People said, okay, according to our predictions, the next solar eclipse should occur during this time in these locations. And so several teams, by land, air, and sea, went to these several locations on the Earth where they could observe a total eclipse. And they each took photographs of the sun as it was being eclipsed, which is shown here in the center. But if you look closely, you'll see these faint labels here that are actually labeling the locations of known stars cataloged at that time by other people. And so they were able to determine, all right, this star is located here, this star is located here, 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 etc. And so they took the actual numbers of the locations in the sky, longitude, latitude, and so on. And then, once they had those measurements, they then compared those with the cataloged measurements made when there's no eclipse. And what they showed was that indeed there's actually a consistent systematic shifting of the positions of these stars such that the amounts by which they're shifted is in total agreement with what Einstein predicted. And so it's hard to see this thing on the right here that I actually already showed before. This is a clipping of the New York Times article when it was confirmed by the groups of scientists who made the measurement that Einstein theory was right, that indeed the measurements made during the solar eclipse confirms Einstein general relativity to be correct. And again, for folks who, I think we all have heard of Einstein, right? So in the physics community, Einstein became famous for describing how peculiar the orbit of Mercury was, right? It's known to sort of shift its orbit over time, and Isaac Newton's idea could not explain that. But when general relativity came along, it actually explained it perfectly, and everyone said, in the physics community, Einstein became famous for that measurement. But publicly, as like a cultural icon and as a public figure, this specific result is what made Einstein famous to the public. It was using the solar eclipse as a mechanism to actually prove his idea correct, okay? And in that sense, solar eclipses have actually played an important role, again, in understanding modern physics. Einstein's theory is the prevailing theory. Anytime we test it, it just keeps passing the tests. And most recently, like folks here work on, Einstein's prediction of gravitational waves, one of the major things we study here, was themselves demonstrated to be real and directly measurable only 7, 8, 9 years ago or so. And again, that's like almost 100 years after they were predicted, right? So, and that was all arguably made possible, if not heavily supported by these initial observations with the help of the sun. So again, I'll go ahead and stop there. I'm happy to take questions, but I hope you came around with the idea that the sun is very cool, super important, and there's a lot of fun, wacky history associated with eclipses. So thank you for your time. Appreciate it. Question?
Since we're able to go back, since we're able to predict when these solar eclipses happen, are we capable of going back and try to find like the exact solar eclipse that was the first one ever recorded? Or is that the time span too large?
That's a good question. I mean, I think we have, right, it's a good question because when you want to take a snapshot of the solar system from a dynamical point of view, like, where things are located and how fast they're moving, and then like rewind, so to speak, there is a point where it doesn't become as accurate anymore, for sure. I can't honestly tell you if they can predict that far back accurately enough, but my thinking is that they certainly must have tried, for sure. Because there's definitely a lot of interest in folks trying to reconcile, astronomical events we observe now, but in a different way. And again, there's really prominent examples. For example, one of the famous supernovae that occurred in our own galaxy, I think it's Cassiopeia A, I can't remember which one it is, the one that occurred like many hundreds of years ago or thousands of years ago, for which there's actually like historical records of like, hey, like around this time, we saw this flash in the sky. And this was thousands of years ago. Now though, today, we observe the remnant of that thing, basically. And we see it not as a flash, but rather this like source of radiation that's really fun to look at with different telescopes. So almost certainly people have tried to do that with eclipses, for sure. Yeah, it's a good question. Question?
I do have a question on a very personal side. How did it feel to be the right kind of doctor on the flight when you showed the people?
Oh, yeah, I mean, I definitely made some friends, for sure, because I think the person sitting next to me, she had no clue. So I remember there was like a guy behind me, a woman in front of me, and they were like clearly trying to edge their way forward. And I was like, oh yeah, the eclipse. So I remember trying to look at it, and then the woman next to me was like, what is everyone doing? And I had to tell her, oh, there's an eclipse going on right now, and so on. I was sort of surprised. I'm like, in the news, it was all over the news, right? So I was a little surprised. I was like, you didn't hear about that, really? But it was fun. Everyone would like, I think everyone around me was taking turns, like, hey, take it out, take a look, and stuff like that. It was really fun. So yeah, I was grateful that I didn't miss it. I remember thinking, I think my flight was even delayed, and I was supposed to originally get to Pittsburgh as it was happening, but my flight was delayed, and I was like, oh, I'm going to miss it in Pittsburgh. But I saw it on the flight, and that was cool too. So yeah, thank you. Any other questions? Again, I'm happy to stick around if folks want to chat or ask other questions, for sure. But sorry.
So in gravitational lensing, like, is it like the gravity of the object that's warping the light? Is that like what?
Yeah. No. So the idea is that, yes. So the long story short, yes. The thing that is lensing the light, so to speak, causing it to bend its trajectory, is gravity. Again, in Einstein's mathematical description, it has to do with the fact that space and time are warped, and light's trying to follow a specific path, but it's following a warped path, and so as we observe it, it'll bend, basically. So, and again, that has to.
In your graphic, you had like it bent.
Right.
Like the actual, but like the apparent is straight. So is that because like space time is curved and it's going in a straight line? Like, because the apparent position, the true position is like the curved space time.
Right. Right. So this straight line here is just the projection of what we would observed, where we observed it to be, basically. Okay. Like so for instance, if the sun wasn't there whatsoever, and the star was in its true position and emitting light, we would see a straight shot from here to here, right? But because, again, light emitted in this direction, as an example, again, if it approaches close to the sun, it'll actually warp slightly, such that when we observe it here, it would have looked like it came from this direction instead, basically. So yeah, it's a definitely a funny way to visualize what the presence of not just the sun, but any massive body does to the way light can kind of go through it or bend around it. And I think last time Sean when he gave his talk on black holes, showed an example of what like this effect in massive, supermassive black hole systems, where the gravity is so extreme that light, due to a disk of accreting matter onto this, like the black hole that's behind the black hole relative to us, actually gets lensed such that it appears as if it's coming like not behind, so to speak, but like actually kind of on top, because it just looks like this donut-y kind of shape, basically. Yeah, basically. And again, in those cases, because the gravity is so strong that it's actually literally bending the light really strong. I didn't even mention the numbers, but this bending is tiny. Like the amount by which the angles of the positions change is like almost one, like, you know, like I don't even know how to describe it in simple words, but it's like seconds of arc, as they say in the lingo. It's like tiny, like fractions of a degree, basically. So it's not very big at all. But for a supermassive black hole, it's quite dramatic, for sure.
So you would have to use like special instruments to detect this, but for a supermassive black hole, you could maybe look at the image and see
Yeah,
the
but,
raw effect.
and that's what people have done with the Event Horizon Telescope. They literally just created an image, so to speak, of the black hole and tried to see what was around it, and they saw something that you could emulate with there being an event horizon and the strong gravity causing it to look kind of warped and funny, basically. Question?
Does the sun like warp itself like?
That's a really good question. Yeah, there is such a thing as self-lensing for sure. With the sun, again, it's not as compact as a black hole, for example, and so the gravitation around the surface of the sun itself is strong, but it's not as strong as a black hole where you would see all these kind of funny, you know, like self-warping effects for sure. But yeah, in theory, it does happen. It's just very, very weak for sure. Question?
Do other planets in the solar system experience solar eclipses? They're the same.
Yeah, in principle. Yeah, right. Yeah, other planets themselves have eclipses because you need a moon basically to do that. At least one, and you know, Jupiter, Saturn, they have tons and tons of moons. So in theory, yeah, they do. I can't tell you when they'll happen, but.
But they've never been observed by probes.
Sure. Yeah. Yeah. As far as like the actual patterns of eclipses on different planets, no, I don't think so. I mean, people do observe planets and their moons totally. In fact, there was something in the news about Io, like one of the moons of Jupiter, like a few weeks ago, I think. Super cool stuff. Like there being a lake of lava, an ocean of lava underneath it. I don't know. But yeah, as far as eclipses go, I'm not entirely sure, for sure. Question?
So on the slide with the picture of the black hole and like the multiple stars around it, or sorry, the picture.
Oh, yeah. This one?
Yeah.
Yeah.
So did they use the stars more at the bottom to predict the real location of the stars at the top that are affecting by gravitational lensing, or are all the stars affected by gravitational lensing to some degree?
The last thing is what you said is true. All of the stars in proximity to the sun undergo this lensing effect, depending on how far away they are, so to speak, from like the sun, at least as projected onto the sky. And so it's more the effect that when the sun, you know, months later when the sun is not in that direction, the stars have some position, right? And because there's no sun in between them at that time, you can measure their positions, call them the true ones, and then when, you know, 6 months later when the sun is kind of in that direction on the sky, in this case during an eclipse, they redid that experiment. They just said, all right, here's an eclipse, here's the stars around them, let's measure their positions again, and then they just did the comparison. All right, when the sun was elsewhere versus the sun was here, what were the shifts in the position, if anything? And they all showed a shift in position such that it was consistent with what Einstein predicted to be the warp, you know, the shifting in position due to lensing, basically. Yeah. Question?
And so with this picture and like the curve, all those stars would be closer to the sun than they look in the picture?
I believe that's the right way to look at it. Yeah, I think so. Yeah, the idea is, is that not right? No? They would be farther out?
Yeah, like common sense. I'm thinking
Yeah, I'm trying to think.
the like curved picture made it look like
Right, yeah, I think I had it inverted in my head too. But you have the right idea though, for sure. Yeah. Question?
Would it be possible or like worth us trying to put like some kind of telescope or instrument in a position where like Earth can be casting an eclipse upon that instrument for us to like see the sun, like to like look at data?
Sure. So historically, I mean, I would say these days that technology, like that probe I showed that's actually orbiting the sun, the technology is good enough where we can actually launch probes or satellites essentially to the sun, and not that they get as close as possible, but not that they get so close that they touch the surface, but when you look up the Parker Solar Probe, you'll oftentimes see articles that say, oh, this probe is going to touch the sun, so to speak. We can actually send things to be that close, and or at least close enough to be like within the orbits of Venus or Mercury and so on. And so in that sense, it's not like eclipses themselves, because we have the technology to do that, the eclipses are not as useful as they used to be in that sense. They're more fun and culturally interesting than being modern tools, so to speak, for science. I mean, again, historically, they were really important, right? But again, I mean, maybe even, like if you look closely, a lot of these figures, you'll see like really, from the Earth, you can almost certainly take all sorts of data during these moments. So because satellites cost so much money to launch into space, it's probably not financially feasible to create something just to do that when we can send things to the sun itself. But who knows? People are creative, and maybe there'll be a good reason to do that at some point, for sure. Yeah. Question?
This is a really dumb question.
No, it's fine.
So if I lived on the light side of the moon, the Earth would potentially eclipse the sun, correct?
During a lunar eclipse.
Right. Yeah. No. Sure. I mean, I think you're asking if you lived on the light side of the moon.
Yeah, but the Earth would get in the way between
Sure.
the moon
Oh, yeah.
and the sun. So would there be any value of us putting instruments on the moon to capture that kind of total earthly eclipse
Right.
and get measurements?
I mean, so a lot of people, there is definitely lots of folks who want to study the atmosphere of the Earth. And I can imagine that if folks ever think of doing something like that, it might be to see if we can study the atmosphere of the Earth somehow. There are people who want to put instruments on the moon. There's all this talk of people wanting to put a radio telescope on the moon. Radio telescopes like the one at Green Bank, for example. They want to put dishes on the moon so that we can basically observe the cosmos, but in an environment where it's much colder, which actually affects the electronics of the telescope and so on. But if and when folks do that, it probably wouldn't be necessarily to observe the eclipse. Although, again, there's lots of folks I know who want to make sense of atmospheres of the Earth or Earth-like planets and so on. And so maybe one day folks will find that an interesting and worthwhile thing to do. But while there is a push to put things on the moon nowadays, it's not so much for studying like lunar eclipses on the moon itself, I think. But again, it's a neat idea, totally, for sure. And a great question. Thank you. Question? Does lensing affect the spectrum of the light? So for the most part, that's a good question. So for the most part, it's not like whenever we study this sort of effect in classes here in physics, they don't tend to depend per se on, I'm trying to think of the equation in my head. They don't necessarily depend on where in the spectrum you're looking at, I think. It affects sort of light all the same in that sense. There are all sorts of really interesting phenomena that can actually lead to these really interesting shifting or warping of the spectrum itself, but that has more to do with the way in which the light interacts with plasma as opposed to just gravity itself. And we see effects like that in all sorts of environments in the universe, for sure. But lensing itself will just take a ray of light or a photon, as they call them in physics, and it'll bend it basically depending on how massive or how much stuff the lens itself has, basically. So the key thing there is not so much the wavelength or frequency of the light, but rather how much stuff does the sun have to cause that warping to begin with, for sure. Thank you. Good question. One more question, maybe? All righty. Well, no, thank you all for those questions. It was awesome. Again, from my understanding, there will be a game. So please do stick around and hang out and have fun and chat. I'll be around for a little bit longer as well. So again, thank you all for coming. And hope you had fun.
All right, everyone. So we prepared a very fun Kahoot quiz. So the winner will get a special prize. So if you want to participate, please do join. I'm gonna pull up the Kahoot right now.
Cheers, Joe. Thank you. I didn't touch it.
No, you're good.